Mr. Moore's math class! Good afternoon, guys, and welcome to Mr. Moore's online flip classroom. Now guys, today we're going to look at how to sketch the graphs of cubic functions but in power function form. Now cubic functions look just like this and can be represented by the equation y is equal to x cubed. Now in power function form, the general equation is something that looks like this. And if you're looking at it and thinking it looks familiar, well it actually does, because it's just like quadratic functions that were given to us in power function form. Now of course our a, our b and our c values can always change the shape of the graph. So let's now have a look at an animation that explains just how these work. So let's check it out.
So as I said before, today we're going to have a look at cubic functions in power function form. Now the first thing we need to take into consideration when looking at these is the general equation, that is y is equal to a bracket x minus b cubed plus c. Now if you have a look over to the left, the basic graph of y equals x cubed is starting to form. That is, every point along the x-axis is being cubed, and this tells us how high up along the y-axis the graph is. Now when looking at cubic functions in power function form, we need to consider the effects of a, b and c when substituting into the general equation. So what we're going to do is have a look at the effect of a first. Now as you can see by the red 2 out the front of the brackets, I've made my a value 2 in this example, and my b and c values are equal to 0. Now when we substitute in and simplify, we end up getting y is equal to 2x cubed. And as you can see, this is basically double the height of the graph for any given value of x. Therefore, we say that the graph has been dilated by a factor of 2 from the x-axis. Now what happens if we leave our b and c values at 0, but make our a value 1/2? Well, we end up getting y equals 1/2 x cubed, which ends up looking like this. Now if we have a look at the graphs for any given value of x, you can see that the red graph, y equals 1/2 x cubed, is half the height of the blue graph, that is y equals x cubed. Therefore, because the red graph has an a value of 1/2, this makes it appear wider than the blue graph. And in this case, we say that the graph has been dilated by a factor of 1/2 from the x-axis. Now let's have a look at what occurs if the a value is negative. Now as you can see, I've got my general equation written out once again, and I've made my b and c values equal to 0. But in this case, what I've done is I've made my a equal to -1. And of course, simplifying this will get me the equation y is equal to negative x cubed. So let's now have a look at how the negative affects each one of the coordinates that you can see. So, as highlighted by the animation, you can see that the graph has essentially just been flipped upside down. That is, each y coordinate of y equals negative x cubed is the same distance from the x-axis as y equals x cubed. However, it's in the opposite direction. And we call this a reflection in the x-axis. So now I've gone ahead and made my a value equal to -2, once again leaving my b and my c values as 0. Now when I simplify this, I get y is equal to -2x cubed. And of course, when I plot these points, what happens is it gets reflected in the x-axis and then dilated by a factor of 2 from the x-axis. So what you can see is the graph becomes thinner, and it also now goes in the opposite direction. Now why does the red graph appear thinner? Well, it's because for any given value of x, it is twice the distance away from the x-axis as what the blue graph is. Now, this is because the magnitude of the a value at the front of the x cubed is equal to 2. Therefore, we would say the graph has been reflected in the x-axis and dilated by a factor of 2 from the x-axis. It's now time to have a look at the effect that the b value has on the graph y equals x cubed. So in this example, I've left my a value as 1, I've turned my b value into 2, and my c value is equal to 0. So therefore, when I go through and simplify, I get y is equal to x minus 2 cubed. Watching the graph move now, you can see that it's moving 2 units over to the right, giving us something that looks like this. That is, the flat part, or in other words, the point of inflection, is at the coordinates 2, 0. So in this example, we say that the graph has been translated 2 units to the right. So let's now have a look at the effect of the b value if we have x plus 2 cubed in brackets. So as you can see, my a is equal to 1 and my c is equal to 0. Simplifying it down gets me y is equal to x plus 2 cubed. Now if you watch the graph over on the left hand side of the screen, you'll see that it's about to move 2 units over to the left. That is, the new coordinates of the point of inflection will be at -2, 0. Hence giving us a graph that looks like this. And of course we say that this graph has been translated 2 units to the left. Alright, so now let's have a look at what effect the c value has on the graph. So in this example, I've made my c value equal to 20, I left my a value as 1 and my b value as 0. When simplified, this gets me y equals x cubed plus 20. Now if we have a look at the graph now, what you can see is that all of the dots move up 20 units. This means that my point of inflection would now be at the coordinates 0, 20, and we say that this function has been translated 20 units upwards. Alright, so what if the c value is negative? Well, let's find out by substituting in c equals negative 15, leaving our b value at 0 and our a value at 1. Now when we simplify this, we get y is equal to x cubed minus 15. As you can see by the dots moving, every single coordinate along the line has been moved down 15 units. And therefore we say that the graph has been translated 15 units down. And to get the now. As you can see in this case, I've made my a value 2, my b value 1, and my c value equal to negative 16. Now when sketching any type of graph, I recommend that you have some form of starting point. In terms of cubic functions, what I recommend you use is the point of inflection for this starting point. And this point of inflection can always be obtained from your b and your c values. So in this case, the point of inflection will be at the coordinates 1, negative 16. Now how's this happen, you ask? Well, it's because our original point of inflection was at the coordinates 0, 0, as highlighted by the red dot. And of course, we know that from our b and c values that the whole graph has been translated to the right 1 unit and down 16 units. Therefore, our new point of inflection will be over to the right 1 unit and down 16 units, placing it at the point 1, negative 16. Now, of course, when sketching any type of graph, we need to find the x and y-intercepts. So to find the y-intercept, we make x equal to 0. As you can see here, I've written out the equation first of all. I've then made x equal to 0. Then I've gone 0 minus 1 is equal to negative 1. Negative 1 cubed is equal to negative 1. 2 times negative 1 is equal to negative 2. And negative 2 minus 16 leaves me with y is equal to negative 18, placing my y-intercept at the coordinates 0, negative 18. And of course, once you've done this, you go through and plot it on the graph as you can see here. So finding the x-intercepts now, I make y equal to 0, but before I do that, I write out the equation in the line. Then I make y equal to 0. Now what I need to do is use inverse operations to solve. So I add 16 to both sides, leaving me with 16 is equal to 2 bracket x minus 1 cubed. I then divide both sides by 2, leaving me with 8 is equal to x minus 1 cubed. I then do the cube root of both sides, leaving me with 2 is equal to x minus 1. And I add 1, leaving me with 3 is equal to x. This means that my x-intercept is at the coordinates 3, 0. And of course, once again, I plot this on the graph. So now that I've got my point of inflection and my x and my y-intercepts, what I can do is go through and sketch the graph. And in terms of what transformations have occurred, well, it's been dilated by a factor of 2 from the x-axis. It's then been translated 1 unit to the right and 16 units down. And of course, because all of our dots are finished on our line, we know that we've actually sketched our graph correctly.
So it is just like quadratic functions where the a value is going to affect the dilation factor as well as any reflections that might take place. And the b value is going to affect the horizontal translation of the graph, and of course the c will affect the vertical translation. And the b and c values are going to give us our point of inflection. Now guys, what we're going to do is we're going to have a look at a quick worked example on how to work with the graphs of cubic functions in power function form. So let's check that out.
Alright guys, so as you've seen, today we're having a look at how to work with graphs of cubic functions in power function form. Now if we have a look all the way over on the left hand side of the screen, we've got the graph of the basic cubic function set out here, that is y equals x to the power of 3. Now if you have a look, the graph of the cubic function starts off really steep. It comes into a point here at the middle where it's actually flat, so therefore if I was walking along this, it would be a really steep hill going up. Then I get to this middle point where it's actually flat ground, or the gradient 0, and then as I continue along again, it gets steeper and steeper going up. Now this point here where the gradient is 0, or where the graph is flat, what we call that is our point of inflection. Or POI for short. Now like I said, this is the point where the gradient is equal to 0. Now this graph of your basic cubic can actually be changed in a number of ways, and that can be modelled by the general rule y equals a bracket x minus b cubed plus c, as you can see up the very top here. Now our a, our b and our c values, as you've already seen in the animation, will affect the shape of this graph. For example, our a value is going to affect the dilation factor and whether or not it's a reflection in the x-axis. So let's have a look at our a value first of all. Now if our a value is greater than 0, we're going to get graphs that look like this, that is where it goes up as you go from left to right. Whereas if our A value is less than 0 or negative, you're going to get graphs that go down as you go from left to right. So if we have a look here, we've got our red graph is y equals 2x cubed, our blue graph is y equals x cubed, and our graph is y equals 1 over 3x cubed. All of these are positive A values, that is positive numbers out the front of the x cubed, therefore the graph is going up. For this one here where we've got A is negative, that is A is less than 0, as you can see here, all the numbers out the front of the x cubed are negative. Negative 2x cubed, negative x cubed, negative 1 on 3x cubed. And as you can see, these graphs are all going down as you go from left to right. And what that means is there's been a reflection in the x-axis. That is, all of these sections that you can see here have actually been reflected up to there. And all of the sections that you can see here have been reflected down to here. Now the other effect that A can have is it can actually affect the width of the graph. Now if the magnitude of A is greater than 1, so for example 2, 3, 4, 5, 6 or whatever else, the graph becomes thinner. Now what I mean by the magnitude is even if A is negative 2, the magnitude is 2. You only worry about the positive value. So if A is greater than 1, or if the magnitude of A is greater than 1, once again 2, 3, 4, 5 or whatever else, the graph becomes thinner. If the magnitude of A is between 0 and 1, so therefore a fraction like 1 on 4 or 1 on 5, the graph becomes wider. So let's have a look here. We've got a graph of 1 on 3x cubed and negative 1 on 3x cubed. As you can see, the graph here is wider than your normal y equals x cubed graph. And like I said before, if A is less than 0, you get a reflection in the x-axis. Now if we have a look at the B and C values, these affect the graphs in another way. That is, our B value is going to affect the horizontal translation and the C value is going to affect the vertical translation. Now if we have a look here, we've got the graph y equals x minus b cubed plus c. If it says minus b cubed, what happens is the graph moves across to the right b units, so it's moving across b units. And the plus c moves it up c units, so our point of inflection is at the point b, c. Having a look at the graph over here, we've got x plus b cubed minus c. So the plus b cubed means it moves across in the negative direction through b units, and negative c means it moves down c units. So this here is negative b, c. So in summing up, the effect of b, if you have something like x plus b cubed, like you can see down the bottom here, it translates to the left b unit. Or if you have something like x minus b cubed, it translates to the right b units, such as what you can see up the top here. Now for the effect of c, if c is greater than 0, it translates up. So that is, for example here, c is a positive, so therefore the graph goes up. Whereas if c is negative, or c is less than 0, the graph translates down c units. That is, in this example where you can see c is a negative, the graph has gone down. And what you can do is you can essentially get the point of inflection from these values, your b and your c.